This is just an introduction to sine waves, and it kind of relies on understanding functions and charts and coordinates and that kind of thing. If you want to know more about those or brush up on them, I do have some other videos for those on the mathmusicandmore.org. Just take a look at the math things. But anyways, for sine wave, we'll start by talking about a unit circle. And a unit circle is called that because it has a radius of 1, and it's a circle. And the question is, what is the significance of that? Well, you'll see actually why it's significant. It's really fascinating how a circle is really the basis for sine and cosine waves. Very interesting. In this particular case, I've highlighted a particular point on the circle. In this particular spot right here, it happens to be at 30 degrees, measured from here and then measured from the right side of this graph. And if you notice, I've dropped a red line down vertically. It turns out that sine wave is effectively defined by the height of this side of the triangle. So, and the input to the sine function, this x right here, is actually the angle. So in this case, this is not x and y this way. In this case, x is the angle, and y is actually the height. So y is still the usual thing, which is the height. But the input here, x, really should be something like alpha. In fact, I'll probably redo that. So the sine of 30 degrees is 0.5. That means that the height from here to here is 0.5. And I've set this up so we can kind of look at some different angles and see how the red line changes with different angles. If you notice, it starts out with sine, it starts out at 0. There's no height. So the sine of 0 is 0. And as you climb in angle, the value goes, it works its way up to 1. But if you notice, it's not going straight to 1. It doesn't run like this. It runs around the circle. And that is the key to the whole thing as far as the shape of the sine wave goes, because it's going to follow this shape, which is governing the height of the red line. So as I go along like this, you notice that the red line at 90 degrees kind of peaks out at 1. And if I keep going, the red line starts getting shorter again. So it kind of peaks out up here. And then it starts coming back down. The other thing you'll notice here is there's symmetry. Whatever happens over here, the same thing happens over here, left and right. So from 0 to 90 degrees, and then from 90 back to 180 degrees, or on to 180 degrees, the way that the height of the red line behaves will be kind of the mirror image of this side. Keep going. Now what happens when I get past 180? Well, similar thing happens, but if you notice, it's drawing down below now. So now the y is negative. But the shape is the same because it's governed by a circle, which of course is not changing shape. So with the same kind of thought process of everything we've done here, you can see that if you get to this angle down here at 270, this is as negative as it's going to get. After this, it'll start coming back up again towards 0. So if you kind of watch the red line as I go, you start to sort of feel the cyclic nature of the sine wave. You get to see how it kind of climbs and falls, but it doesn't do it linearly. It doesn't do it evenly. It's not a triangle this way. So what I'm going to show you now is the sine wave. If you were to take these red heights, these values at each angle, and instead of just watching them move around the circle, if you were to instead graph them with the angle going off to the right. So now with every angle, I can go over here and then put the height up. The height of the red line draws the sine wave. So that's what's really interesting about the sine wave, is it is intimately tied to a circle. You basically can't have a sine wave without a circle. The symmetry of that is really amazing. And if you remember, we talked about how it peaks out right here, 90 degrees. You can see, sure enough, sine wave peaks out at 90 degrees. You can also see it returns to 0 right at 180, which is the height. So this is fascinating because that means when you see sine waves, you should be thinking circles. I'm going to go ahead and I'll throw in here cosine, because cosine, it turns out, is instead of the vertical of this triangle, it's the horizontal. So the cosine of the 30 here is 0.866, which I believe is square root of 3 over 2. I'm trying to remember. And if you do the exact same thing we did before, but keep track of the blue line, and imagine measuring the length of the blue line every time you had a different angle, you would see the blue line goes from a maximum at 0 degrees. Here it's maxed out at 1. And as I walk my way up to 90 degrees, the blue shrinks down to 0. But clearly, the way the triangle is mapped on this circle is symmetrical, but we're just looking at the other side of it. So it turns out you wind up with the same curve, but you wind up with it shifted by 90 degrees. So sine and cosine are the same thing, but they're just shifted because of the definition of where they come from. So that's just a sort of a, just a little preview of sine waves and similarly cosine waves and how they relate to the unit circle. And tangent is just a mathematical construct of sine divided by cosine, which I won't bother talking about. But the next thing that we'll talk about is the derivative of a sine, which starts getting very fascinating when you start thinking about what a derivative means. Thanks for watching, and talk to you later.